Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, we are from Group 3 and with our lecturer Dr. Henry Hendrawarti, SAMSE, we will try to explain about waiting lines and queuing theory model. Learning objective of waiting lines and queuing theory model chapter is first, describe the trade-off curve of cost of waiting times and cost of service. Second, understand the three parts of queuing system, the calling population, the queue itself, and service facility. Third, describe the basic queuing system configuration. Fourth, understand assumption of the common models deals with in this chapter. And the last is analyze a variety of operating characteristics of waiting lines. Queuing theory itself is a mathematical study of waiting lines. It is one of the oldest and most widely used quantitative analysis. There are three basic components of queuing process. First is arrivals, second is service facility, and then the actual waiting line itself. The analytics model of waiting lines can help manager evaluate the cost and effectiveness of service system. Most waiting lines problems are focused on finding the ideal level of service a firm should provide. In most cases, the service level is something management can control. When an organization does have control, they often try to find the balance between two extremes. There is generally a trade-off between cost and providing service and cost of waiting times. A large staff and many service facilities generally result in high level of service but have high costs. And so, having the minimum number of service facilities keeps service costs down but may result in dissatisfaction customers. Service facilities are evaluated on their total expense cost, which is the sum of service costs and waiting costs. Organizations typically want to find the service level that minimizes the total expected cost. This graphic shows queuing cost and service level. As we can see here, cost of providing service are in line with cost and service. While the cost is high, also the service level. But it is the opposite for cost of waiting times. While the cost is high, the service level is low. When cost of providing service line and cost of waiting lines cross each other, it creates optimal service level that is the lowest cost in total expected cost. Take example from Three Rivers Shipping Company. Three Rivers Shipping Company operate a docking facility on the Ohio River. An average of 5 ships arrive to unload their cargo each shift. Ideal ships are expensive. More staff can be hired to unload the ship, but that is expensive as well. Three Rivers Shipping Company want to determine the optimal numbers of team of staff door to employ each shift to obtain the minimum total expected cost. As we can see from the table, the first step, they give average number of the ship arriving per shift, and then the average time each ship wait to be unloaded, and they times it to find total ship hour lost per shift. After that, they estimate cost per hour of idle ship time. Then, by times it together again, they found the value of ship lost time or waiting cost. After that, they found the stiff door time salary or service cost. The waiting cost plus their service cost, they can find the total expected cost. Characteristic of queuing system: service time distribution. Service pattern can be either constant or random. Constant service times are often machine controlled. More often, service times are randomly distributed according to a negative exponential probability distribution. Analysts should observe, collect, and plot service time data to ensure that the observation fit the assumed distribution when applying this model. 4 basic queuing system configuration. First is the single-channel, single-phase system, where there are only one service facility. Second is single-channel, multi-phase system, where there are 2 types of service facility. And Third is multi-channel single-phase system, where there are 3 different service facilities. And the last is multi-channel multi-phase system, where there are 2 types of service facility and 2 different service facility. Characteristic of queuing system: service time distribution. Service pattern can be either constant or random. Constant service times are often machine controlled. More often, service times are randomly distributed according to a negative exponential probability distribution. Analysts should observe, collect, and plot service time data to ensure that the observation fit the assumed distribution when applying this model. Identifying models using Kendall notation. D.J. Kendall developed a notation for a queuing model that specifies the pattern of arrival, the service time distribution, and the numbers of channels. Specific letters are used to represent probability distribution. AMS is represent Gaussian distribution for numbers of occurrence. D represent constant rate, and G represents general distribution with known mean and variance. Identifying model using Kendall notation. A single channels model with Gaussian arrival and exponential service time will be represented by MM1. If a second channel is added, the notation would read MM2. A 3-channel system with Gaussian arrival and constant service time would be MD3, and a 4-channel system in Gaussian arrival and normal distribution service times would be MG4. Single channels model, Gaussian arrival, exponential service time, or MM1. When the assumption model are met, we can develop a series of equations that define the queue's operation characteristic. Queuing equation. Lambda symbols mean number of arrival per time period, while mu symbols mean number of customer or units served per time period. The arrival rate and the service rate must be defined for the same period. Single channels model, Gaussian arrival, exponential service time, or LM1. As you can see here, there are 7 different equations. The first is the average numbers of customer or unit in the systems, or L. Second is the average time a customer spend in the system, or W. Third is the average numbers of customer in the queuing, or L key. Fourth is the average time of customer spend waiting in the queue, or W key. 5 is the utilization factor for the system, P, the probability the service facility is being used. 6 is the present ideal time, or P0, or the probability no one is in the system. And the last is the probability that number of customer in the system is greater than key, or Pn lower than key.
So here I wanna explain about the Arnold's muffler shop case. The Arnold's mechanic can install mufflers at a rate of 3 per hour, and the customers arrive at a rate of 2 per hour. So the lambda is equal to 2 cars arriving per hour, and the mu is equal to 3 cars serviced per hour. To calculate how many cars in the systems on average, the formulation is lambda divided by mu minus lambda, and the calculation shown as that it is 2 cars in the systems on average. And if we want to calculate how many hours that an average car spends in the system, the formulation is 1 divided by mu minus lambda, and the calculation shown it is 1 hour that an average car spends in the system. And this is for the calculation of the cars waiting in line on average, and this result is 1.33, and the average waiting time per car is 40 minutes, and the service busy is 0.67, and the probability that there are 0 cars in the system is 0.33. And here are the probability of more than k cars in the system. The formulation they use is P n bigger than k is equal to 2 divided by 3 times k plus 1. So here are the POM-KM solution and analysis for the Arnold-Muffler shock case. And the first is we choose the waiting lines and choose the exponential service times. And for the title, we add it as an Arnold Muffler shock case. And for the cost analysis, we choose no cost and click OK. Here we need to add the arrival rate or lambda and the service rate or mu. So according to the case, the lambda is 2 cars arriving per hour and the mu is 3 cars service per hour. So we add it here 2 and 3 and then we click solve. So from the data result, we can see that the average server utilization or when the server is busy is 0.67 and the average number in the queue is 1.33 and the average number in the system, which is how many cars in the line, is 2. Average time in the query is 0.67 or equal to 40 minutes or equal to 2,400 seconds. And the average time in the system is 1 equal to 60 minutes and or 3,600 seconds. From the solution above, also we can get the table of probabilities. So here are the table of probabilities, and as we see that it is the same solution, the same result as the PPT shown. And from the solution, again we can see the graphic of probabilities. So here are the graphic of probabilities of Arnold after shock case. Yeah, for the POM-KM solution, it is pretty much the result of the Arnold-Muffler shock solution.
Conclusion: waiting lines and service systems are important parts of the business world. In this chapter, we described several common queuing situations and present mathematical models for analyzing waiting lines following certain assumptions. Those assumptions are that first, arrivals come from an infinite or very large population. Second, arrivals are Poisson distributed. Third, arrivals are treated on a first-in, first-out basis and do not bulk or vintage. Fourth, service times follow the negative exponential distribution or are constant. And the last one, the average service rate is faster than the average arrival date. The model illustrated in this chapter are for single-channel, single-phase, and multi-channel, single-phase problems. After a series of operating characteristics is computed, total expected costs are studied. Thank you for your nice attention and goodbye!